Okay, so that's how I find the eigenvalues. How do I find the eigenvectors? Well, what did we do? We looked at a minus lambda I times x is equal to 0. And I know that there will be non-trivial solutions when lambda is equal to 4 and when lambda is equal to -1. So let's look at the first one, lambda equal to 4. So I'm looking at the homogeneous system a minus 4 times I, x is equal to 0. That is going to be the matrix 1, 3, 2, 2, minus 4, 0, 0, 4, times x is equal to 0. And when I do that subtraction, I will get -3, 3, 2, -2 times x is equal to 0. And what I'm looking for are all of the non-trivial solutions. So I need the reduced row echelon form of -3, 3, 2, -2, which is going to be equal to, and please check this, it's 1, -1, 0, and 0. And since my vector x is in R2, I think of it as being x1 and x2, and so I solve it by looking at x1 and x2. x2 is a free variable, x1 is equal to x2, and so then that implies that my solutions are the span of 1, 1. So another definition, all of the eigenvectors are linear combinations of 1, 1. We call this an eigenspace. It is the set of all possible eigenvectors for a particular eigenvalue, in this case equaling 4. So we still have to go to -1, but let's see if we can understand a little bit about what's going on with these eigenvalues and eigenvectors. So I've now decided that when lambda is equal to 4, I have all linear combinations of 1, 1 being eigenvectors. So let me just pick a linear combination. How about if I just pick -2 times 1, 1, and I just randomly pick -2. That's going to be -2, -2. And if everything that we did here is correct, then this is now an eigenvector. And so I can check this. Is it going to be the case that a times this x, is that going to be equal to 4 times x? Easy enough to check. A was 1, 3, 2, 2. And if I multiply that by -2, -2, then multiplying this row by this column will give me 1 times -2 plus 3 times -2. That's going to be 2 minus 6 is -8. And 2 times -2 plus 2 times -2 will also be -8. And then what I can see is that that is in fact 4 times -2, -2. So this works. This is going to be an eigenvector. There's an infinite number of eigenvectors. It's all of those. And since it's the span of a set of vectors, that's going to make it a subspace of R2. All right, so there were 2 eigenvalues. We need to look at what happens with the other one. The other eigenvalue was lambda equal to -1. I'm going to do the exact same thing as I did with 4. I'm going to look at the matrix A, 1, 3, 2, 2. I am going to subtract -1 times the identity, 1, 0, 0, 1, and look at that as being multiplied by x and being equal to 0. So this would be 1 plus 1 is 2, 3, 2, and then 3. And so yet again, trying to find the solution to the homogeneous system, I want the reduced row echelon form of 2, 3, 2, 3. If you check, that will be 1, 3 halves, 0, 0, which means that in my solutions x1 and x2, x2 is free and x1 is negative 3 over 2, which means that my solutions are going to be the span of negative 3 over 2, 1. Again, we should check this. So let's pick, I'm going to pick um, 2 multiplied by negative 3, 2, 1, just so that I get rid of the fractions. So this would be negative 3, 2. And so this is in the span of that vector. So if everything that we did here is correct, then this should be an eigenvector. And how do we check? We check to see, is A times X equal to lambda, which in this case is negative 1, times X. All right, so let's check. 1, 3, 2, 2 times negative 3, 2. That would be 1 times negative 3 plus 3 times 2 is negative 3 plus 6, so that's 3. And then 2 times negative 3 is negative 6, plus 2 times 2 is negative 6 plus 4 would be negative 2. And sure enough, that is equal to negative 1 times the original vector 3, 2. So what did I find? It seemed like a lot, but it really wasn't that much. Just to review what I did here was I started out with A, which was 1, 3, 2, 2. And then we evaluated the determinant of A minus lambda I. We set that equal to 0, and it was a polynomial. And what we found was that the roots of that polynomial were 4 and negative 1. Then I looked at lambda equal to 4 and found that the solutions were the span of 1, 1. And then we looked at lambda equal to negative 1 and found that the solutions were the span of negative 3 over 2, 1. So we have eigenvalues of 4 and negative 1, and then the eigenvectors are all of the vectors that fit into the span of each one of these spaces. And so in this case, there was one vector in the basis for each one of these spans. Sometimes there might be two, and we will see plenty of examples of things like that.